Hi everyone, hope I am audible. So today we will be discussing the problems contain, guessing game, DIFVAL and perfect partitions, and hopefully at the end some strategies for the challenge problem as well. So let's start with this problem, the delicious cake. Um, so it's a geometry problem. You are given n points and 2D points, x1, y1, x2, y2, and so on. Now you have to kind of make layers in the cake. So these endpoints are said to be a part of a cake. So you have to make layers. What are the layers? Layers is just any polygon that you can draw using any subset of the points with the following criterias. So there also you are given a candle. Now you will actually have q queries where in each query you are given a candle and you will have to report the number of layers. So what are the conditions for the layers? The candle must lie strictly inside it, so not on the border or anything. um, each of the chef's endpoints that lie strictly inside some layer must belong to some other layer. So that basically means that there should be no free point, like every point should kind of belong to one of the layers, and no two layers may touch or intersect. And it and what you have to do is, for a given candle point, you have to distribute all the points into the maximum number of layers, and basically you have to output that maximum number of layers here. So let's try to get a scenario of what we are dealing with. So let's say these are the several points that are given to us. So let's say the candle point, so it's basically, it comes in a query. So let's say in a query the point that is given is here. Now one possible layering that you can do is something like this. Remember that it does not have to be a convex polygon, it can be any polygon. Oops, not, wait, the last line was wrong. Yeah, so in this case there is only one layer. Now you could have also made the layers like this. Right? So in this distribution, you would have got two layers. So this is better. So how do we proceed with the problem? One thing that you can try, since Q is relatively small, so the number of queries is given to be 2000. So one initial thought might be that with this point, I want to, like with the candle point that is given, I want to find the smallest polygon that is enclosing it. But even with this as a starting point, it's very hard to define as to what a smallest polygon is. I mean, is the area of the polygon smallest, or do you want to do something else? Like, I mean, area of the polygon is smallest is one possible way to look at it, but maybe there is some other criteria that is better, right? So because there could have been a point like this, there could have been a point, let's say that this was not the candle point, let's say uh, this was the candle point, okay, and there was a point something like this. So then if you choose the smallest area one, you might have a triangle like this. Sorry, it all the way it comes to here and then it goes to here. So this might actually have this area is probably lesser than this area. I mean, all the drawings are obviously approximate, but anyway. But if you chose this as your first layer, as your innermost layer, then you won't be able to choose any more layers, because there is no way this point and this point will ever get connected in a layer, because for it to contain this red point, then it must have been something like this. I mean, it cannot go all the way around here, right? You have to join them with straight lines, but then it kind of intersects with the inner layer. So choosing the minimum area triangle might not be the best idea. So from here, maybe you will get the intuition that choosing the innermost, like trying to choose what is the innermost layer which is most closely surrounding the candle point, might not be an efficient way to do the problem. What is a better way? Well, you cannot go from inside outwards, so try to think about what if you formed the outermost layer first. That turns out to be relatively easy. What you can just do is take all the points and form its convex hull, right? So for example, in this diagram, this blue enclosing polygon is the convex hull. This convex hull you can find in order n log n if there are n points. There are a variety of algorithms for this. But yeah, so this you can do. Now what about the rest of the points? Now the key observation here kind of was that, so for a moment, let's assume that whatever layering you do, all the layers will be convex polygons. Okay. And the center point, that is the candle point, was very symmetrically placed, everything in the middle. So how can you form the rest of the layers? Once you form this outer hull, so this is the first hull. After that, remove all these points. So you remove all of these points from your set. So these are no more active points. So not active points. So now what you do is, from your set of active points, you find the convex hull again. So what you effectively do is find convex hull from active points. And let this hull be H. And then for all P that belongs to H, P becomes not active. Right? Not active, inactive, whatever. So basically you had this big set S of active points. Once you put something in the hull, you subtract P from here. Okay. And then again keep on finding the hulls. Now, what had we assumed here? That the candle point was actually very symmetrical. It was totally in the center and so on. So if you kind of find all the convex hulls like this, these conditions are all satisfied. So the candle point is lying strictly inside it, because again, that's our assumption till now. Each of the points that lies inside some layer must also belong to some other layer, because this is also true because every time you are finding the convex hull, so you are finding the largest polygon that takes in everything, and no two layers will touch or intersect. That is also guaranteed. So remember that in this convex hull, you should also take care of collinear points. Collinear points will also be part of this outer hull. You won't skip over them. I'll get back to what strategies you can do to take care of collinear points. And layers must be chosen in such a way that deliciousness of the cake is maximum possible. This is also uh, should be intuitively easy to verify, that once you start taking the convex hull of iteratively of each set of points, the number of hulls that you take is the maximum possible. Now, what if the candle point was not perfectly at the center? What do you do then? So, what if the candle point was not perfectly at the center? Let's say the candle point was somewhere around here. Then this hull is not the appropriate one to take. right? I mean, maybe you could have taken some other hull as your innermost, that would have been better, something like that. But turns out that what you can just do in this case is find out how many layers of hulls this candle point is not inside. So imagine it like this. These are your hulls, let's say. Now let's say your candle point is somewhere here. That means that your candle point is not inside the inner hull, but it is inside all these hulls. So your answer is basically the number of convex hulls inside which the candle point lies. So here, for example, your answer is 3. So you kind of iterate over all the hulls from inside out. When you see that the candle point is contained inside the next hull, you just break your loop, and whatever the number of hulls outwards was, that's your answer. Now, why is this correct? I won't go into a very theoretical proof because I don't know what a very rigorous proof would be. But intuitively, what you can do is anything that is it. So these were your hulls, right? And then this was the point. Let's say. So anything that was in here. So these are also sets of points. So I claim that whatever your optimal solution you might have got, which was not this, if this was incorrect and there was some other optimal solution, then these points would still not be contributing something to your answer. I mean, you can just ignore these points and still get your answer. Why? Because if there was a polygon that used one of these points to form that polygon, then there must have been something here and something like this. The diagram would have looked something like this. But then that means there was a point here, right? This point would have already belonged to this outer hull. So so again, these points will now not be able to form a hull in of themselves because this point is invalidated. So these points will kind of look forward for another point here to complete the convex hull. But again, this was supposed to be part of another convex hull, right? So again, this would have bulged outwards a bit and so on. So effectively, you are making a convex hull here that is including it, but then the outermost convex hull kind of breaks. So it does not really help you. Uh, Hopefully that makes sense. Now, what about, okay, so there's a question, no two layers may touch or intersect. Basically, your convex hull should be like these concentric circles kind of a thing. Your layers cannot be something like this. This is an invalid layer. If you like, this is not possible. That's all what it means. Now, in this scenario, when you're so let me just try it again. So let's say this is your candle point, and there were some points here. Now the question is, doesn't this violate rule 2? Because in rule 2 it said that every point that lies inside a layer must belong to some other layer. So this seems to violate that rule, right? But what you can do is the first layer inside which the candle point lies, you can kind of twist that layer into a non-convex polygon, something like this, and make it include every other point that belong to inner convex hulls. So you don't have to like this logic should be clear in your mind that this is valid. You don't actually have to code this. Only have to code this part, that how many convex hulls does my point lie inside. This part wasn't required to be coded, but it should be clear that it effectively um, maintains this condition as well. Okay, so now this was more or less the entire problem. Now let's maybe discuss, first let me discuss how do you take care of collinear points. So how the one method of doing it is in the convex hull algorithm, what I generally do is I take the leftmost point in your point set as the pivot, and the leftmost bottommost point. So this is my pivot. Now when you are sorting, when you are doing that angle sort, for convex, for collinear points, what you can kind of observe is that if there are 2 points with the same angle from the pivot, okay, so this is a point, this is a point, you additionally sort by the distance. If there are no 2 points with the same angle, then you can effectively just check for collinearity. When in the clockwise function, maybe you do greater than, you just do greater than equal to, like basically for collinearity, cross product can be equal to 0 or it can be greater than 0. Then the points, or like it checks for counterclockwise as well as collinearity. The only important case was when they have the same angles, then you just sort by distance. But then one extra thing that you might observe, this is true for anything that goes below, but when it comes from above, then if you sort this with this, suppose they have the same angles, if you sort this with distance, then this will come first, right? So let's say you are going on building the hull like this and you are at this point, then you want to process this point next, not this point. But that would have been the case if you blindly sorted with distance after the angle was equal. So what you essentially do is you can do two things. You can take everything that is below the pivot and sort them by angle, then sort them by increasing order of distance, and everything that is above the pivot, you sort them by angle and then decreasing order of distance. This is one thing that you can do. Or you can build the lower hull and upper hull separately, like take the pivot here, build the lower hull, take the take the first pivot here, build the lower hull, then take the second pivot here, and then it's kind of symmetrical. You use the same comparator function. This code is elaborated in the testers code. Okay, so let me just read the chats. One point cannot be used by two polygons. No, it cannot be used by two polygons. Collinear points can also contribute to form the same polygon, right? Yes. So whichever hull that you are considering, you must also consider collinear points. That was an important thing, right? Now, second part. So we can build the convex hulls. Now, how do you check whether a particular point is lies within a convex hull? There are several methods to do this. I have linked some of the methods in the editorial. You can, so one of the methods is if there is any polygon, and I think it need not be convex. It could have been a concave polygon as well. It's a much more general method. Let's say you want to check whether this point lies inside. You basically draw a ray from the left. If there are odd number of intersections with this ray and the polygon edges, then that means this point lies inside. So if odd intersections, then it lies inside. If even, then it lies outside. So this is more general and applicable for simple non-convex polygons as well. For simple convex polygons, so there is a ordered log n method, which I have also linked in the editorial. Now, let's see what the complexity of the code could be. You are building n convex hulls again and again, right? So every step might take n log n time. So you might have a overall processing time of n squared log n, right? And so this is kind of the pre-processing step. So pre-process. So n is the total number of points. Actually, in actuality, the complexity will be much lesser, but like since because like if you already selected a bunch of points in your outer hull, then obviously the number of active points is much lesser for the inner hull. But this is kind of the upper bound that you can easily derive. Now, what happens in a query? So in a query, the simplest thing that was meant to pass is for every hull, you kind of just iterate. So there can be up to order n hulls. So you just iterate over all the hulls and then check whether the thing lies inside or not, like the candle point lies inside the hull or not. So that would have taken you n time, and you have overall q queries. So this is the simplest complexity that you can achieve, qn square. I think this was sufficient to pass the problem. But anyway, since it's like theoretically it's qn square, but in actuality it's actually much better. But you can improve this a lot. So one of the things that you can observe here is that which convex hulls do not lie and which lie in like inside which convex hulls the candle point lies or not. That is kind of an increasing sequence, in the sense that there are first some convex hulls inside which the candle point does not lie, and then the rest of the convex hulls contain the candle point. So you can binary search what is the first hull that contains the candle point, and that will take you log n time. So here for every query you can make this n log n qn log n total complexity. You can reduce this even further. Notice that here I have taken that you are checking whether a point lies inside a convex hull in order n time, but you can do this in order n log n. So you could have actually made this q log square n. But again, in the actual problem, you did not need to optimize it to this level. Even qn log n would have passed. Maybe qn square would have also passed. So yeah, I guess that's the entire problem then. Any questions on this? If there are any questions, write in the chat or something. As for resources to learn convex hull, I mean, it's a very popular topic, so just Googling should be fair enough. So yeah. So let me just elaborate on the q log square n again. So for every query, So for every query, what you do is you need to find what is the first convex hull for which the candle point lies inside it. Notice that you can binary search this convex hull. Okay. So let's say you binary search it. And then to check whether a point lies inside a convex hull or not, you can do that in log n time as well. Again, how to do it, I have linked the resources in the editorial as well. So for every query, you take log n time to binary search and then another log n time to check whether the candle point lies inside the polygon. So overall log square n per query, hence q log square n. Right. So let's move on to the next problem. Guessing game. So this problem is extremely ad hoc and not trivial at all. But let's see what we can do here. So for the first subtask, I hope everyone has read the problem already. If not, then a brief would be, it's basically a binary search kind of a problem, but then the grader can lie. Basically, if it's a, so you are given a hidden integer y, and you have to guess it with some x. And if x is greater than y, less than y, equal to y, you get those results from the grader. But then the grader can lie, and the only condition is that it cannot lie 2 times in a row. So in how many queries can you pinpoint what is the hidden integer? So for the first subtask, it follows a simple strategy. She either answers the second, fourth, sixth, etc. truthfully, but she may or may not lie in all other questions. So for the first subtask, you know that basically you can do 2 binary searches, one based on the even. So like you basically make a query and then make a false query, kind of like this, and then you can just binary search, and it will easily work inside 300. So try that subtask on your own, maybe. Um, let's move on to, I am not sure exactly how to, what is the intended solution for subtask 2, but say, basically there are a lot of different possible approaches, and that's why there are these few subtasks, but it's not like there is a particular intended solution for subtask 2. So let's kind of get a better feel of what the problem is. So this is all the possible numbers. Your hidden number is, let's say, somewhere here, but you don't know what it is. So anyway, now what is it that you can do? There are a couple of approaches that I tried when I saw the problem. The first was, maybe we can query at the middle point. Let me use a different color here. So maybe we can query at the middle point, break it into 2, and then somehow find whether this is true or false. But this is very hard to do, because you definitely don't know which is true, which is false. Another thing that you could have tried is along the same lines. Maybe you could, so this is basically partitioning the array into half pieces. Maybe you could partition into 1/3 and 2/3, and then somehow using this small array, you could have got some information out of it. But again, even that is very hard to do. I mean, hopefully everyone has thought about this, and um, it's not sure how you will entirely deduce which region to go into after this. Now the next idea that one might have is, instead of trying to fixate on 1 or 2 queries and trying to jump into one of the selected sections, let's make multiple queries at some intervals. And let's say we like query this, then this point, then again let's say this point, then let's say this point and this point, and so on. Like we query so let me call this point as M, let me call this as L, and this is R. So we have a query string like this, okay, which means that we query here, query here, query here, query here, and then we are guaranteed that if we query in a particular sequence, then we can uniquely identify which of these regions our point must lie inside, whether irrespective of which of them is a lie, which of them is a truth. But even then, and even then, I mean, I basically wrote a brute force code for this. So I tried all possible such query sequences using like querying at each of these intervals. I tried all possible sequences of whether the grader is telling the truth or it's telling the false. But in none of the sequences, there was a common region which stood out, such that whatever the sequence of operations was, that region kind of I mean, so basically every one of these operations gives you a particular set of regions, right? Let's say M gives you either these two regions or these two regions. Left gives you either the last three regions or the first region, and so on. So in whatever, what like among all sequences, if there is a common region among all of them, then obviously you can kind of say that, okay, that means in this particular area, that this is where my number might lie. But again, if you brute force this and generate up to, let's say, 5 or 6 query sequences, even then it's not possible to get such a uh, region, like such a specific region. So now that I know that it's very hard to actually, oops. So now that I know that it's very hard to know that which region in my entire set of possible values my answer lies in, so I cannot fix a region. Now, when you cannot go in the forward direction, it's often a useful way to think, can I go in a backward direction? So here, what is a backward direction? What you can do is maybe try to eliminate a region. Right? Treat this as a multiple choice exam and just eliminate answers. Now, let's think about how we can eliminate answers. It seems like a good idea to first query in the middle only. So let's query there. Let's query at the middle point. And let's say the grader returned us the greater than sign. Now there are two possible cases, right? I mean, case one, the grader told the truth and the actual answer lies somewhere here. So let me also mark the regions. To light. Yeah. So let's say this is region 1, this is region 2, this is region 3, this is region 4. If the grader is telling the truth, then that means the regions where it definitely cannot be is 1 and 2. Okay. Now, what you can do is you can query at this place. So let's, if the grade, so whichever point was kind of, if it was telling the truth, then 1 and 2 are likely to be eliminated. So now query in the midpoint, and let's say the grader gives this symbol, the greater than symbol again. That means one of them, either this or this, is the truth. So if this is the truth, then these two can be eliminated. And if this is the truth, then only one should be eliminated. You don't know which is the truth or which are false, but you definitely know that one of them is true. It might be that both are true. It might be that the first query was true, the second is false. It might be the first is false, second is true. But in both the cases, you are definitely sure that the first region is not valid. So you can definitely eliminate this first region, right? And then your problem reduces to a smaller range. Now, in the opposite case, what if the grader returned this symbol? Again, you know that one of them must be true. So if this is true, then 2 is definitely not possible. And then if this is true, okay, and let's say this is false, that means that this must be true. Then also 2 is definitely not possible, right? So in both the cases, whichever one is true, and if both are true, doesn't matter. In both the cases, 2 is not possible, so you eliminate 2. So you eliminate this region. So now your regions are left with 1, 3, and 4. Note that this is not contiguous. So you will kind of have to maintain ranges for it. So a list of ranges. And when you are finding this midpoint, left, right points, and so on, you have to find them from this range. It's not like you can just do n by 2 every time. You have to find the middle element from this. One question is, what if we get greater at n by 4 and lesser at n by 2? I just discussed that. If you get lesser at n by 2, then and greater at n by 4, then this region is definitely eliminated. Whichever one is true, this region is eliminated. Now the case is kind of symmetrical if the first query was this sign. Okay, I think you meant lesser at n by 2. Sorry for that. So if the grader returns this sign, then again it's symmetrical. You query at the right point. So instead of querying here, you query here. And again, if this is the case, then this part is definitely eliminated. If this is the case, then this part is definitely eliminated. So in all the cases, you make two queries and your search space reduces by 25%. Okay. Now you can do some calculation and you can check that if you run this algorithm, you will need approximately 140 queries to fixate the actual location of the hidden number. Now note that one thing that I forgot to mention maybe is that you cannot use some random tactics that okay, let's just assume that it is somewhere around here and with some probability we will get this and so on, because the grader is adaptive. So adaptive grader means that the hidden number is not actually fixed from the beginning. The grader will, I mean, to you it's hidden, it's still hidden, but the grader might change the number internally. So yeah, so depending on your queries, the hidden number might change. It will still be valid, it will still be a valid hidden number, so that you have not fixed it yet, but yeah. Now 25% query, you get 140 queries for 25% reduction. Now how can you improve this? Because in the last subtask, so this is enough to get you 140 points, but not sorry, this is enough to get you 75 points, but not enough to get you 100 points. So how do we make this better? So one thing that you might think is that maybe we can make the first query somewhere skewed and then try to make the other queries. But notice that like in one of the two cases, you will be removing something much smaller than 25%. Like in one of the cases, so this is why random tactics doesn't work here. If this was a random if the judge was not adaptive and it was already fixed, then you might have said that okay, I query at somewhere around here. Now I know that the chances of it being greater is more. Actually even then I think random tactics wouldn't have worked. Anyway, the point is, if it is greater, then the chances of you removing something significant is very less. You will be removing less than 25%. So that is worse. And since the judge is adaptive, then it will always make you remove something from here. It will never return you this symbol, because if it returns this symbol, then you get to remove greater than 25%. The judge is clever. It does not want you to do that. It wants to make you use as many queries as possible. So yeah, so using exactly two queries to remove something that is greater than 25% does not seem to be very uh, doable right now, because dividing stuff at the middle is kind of the best you can always hope for. So maybe what we could try to do is not use exactly two queries every time, but over let's say n queries, you remove greater than n by 2 into 25%. So effectively for every two queries you remove greater than 25%, but it's not like for every two queries you can do that. So the actual solution, like the full solution here, is pretty neat. What you do is you have your range, right? Now you make the query at the middle, and let's say we get the greater than symbol here. Now query at the 2/3 position. So this should be 2/3 and this should be 1/3. Okay. Now there are again two cases. In the first case, you get a less than symbol. Then how much are you removing? You are removing 2/3 of half, right? So that's 1/3, which is 33%. So in this first case, you get to remove 33% and you are very happy. In the other case, you have this lesser than symbol. I'm actually not sure which is greater than. Anyway, let's say you get this symbol. Now, what do? You definitely know that this is then not true, but how much are you effectively removing here? You are removing 1/3 into 1/2, right? Which is just 1/6, which is just 16.5%. So just as we had feared here, right? You are in the best case scenario, you're removing greater than 25, but in the worst case scenario, you're removing something that is less. Correct? So effectively here you are removing using two queries to remove just 16.5%. So you might think that, okay, but then how is this useful? Here's how. You, after you do this query, you remove this section. Correct? Now is the main part. You use, so for, in our previous cases, we made two queries, we reduced the section and then we again repeated. So this was kind of step one, make two queries. Rather, let's say, let me show it like this. So step one was make a query. Then step two was make another query based on the previous query. And then step three was remove one of the regions. And then step four was return to step one. Now what you do is, instead of step four returning to step one, you kind of make your first query. So this is, let's say, the first query. This is the second query. So this is Q1, this is Q2. Now what you do is you set Q1 equal to Q2, and then S4, you go back to step 2. So what I'm trying to say here is, instead of starting all over again, you utilize this last query that you make. Okay. Now, why is this good? In this section, after you had removed the 1/3 portion, your query is kind of skewed to the left, and the bigger part is toward its tail in some sense. Like if you consider this as the head side and this is the tail side, so you were always making the next query in the tail side, right? Now here we already know that the tail side is the larger part, and here you make the second query at the middle. Okay, let's say like this or this, whatever. I mean, actually you don't make this at the middle, you make it at the 2/3 point. So let's say this is the 2/3 point, this is the 1/3 point. So you make it here. Okay, and then again, if you get this, then you get to remove 2/3 and you kind of start from the beginning, like start from step one again. But if again you just get to remove this 1/3 portion, then in the next step you again treat this as the original first query, and then so after this you will have this section, something like this. So let me use colors to visualize it. So for this section is this part, and this section is this part, right? After the eliminations. So now you already know that at this position you have this kind of a thing, and then you can make a query here again at the 2/3 point. So okay, so one question is, what will you be removing you get if you get a symbol like this and then this? This is never the case, because once you make a query like this, you always query the part that is towards the tail. So you always query this part. So you will have either this case or this case. This case is not solvable. Okay, this is bad. So this case is bad. You either will have this or you will have this, assuming this is the first query. I hope that clears it up. Yeah. So if you kind of go through the math and figure out what the exact complexity is, you will find that effectively, if you kind of go on doing the procedure in when you encounter this second case, then also you will be removing approximately 33% for every two queries. So again, this is not like for every two queries you are removing 33%. You are, let's say, making n queries, and overall you are removing n by 2 into 33%. When you, so every time there is a possibility of you ending up in case 1 or you ending up in case 2. When you end up in case 1, then you remove that 33% and you go back to making the first query from step 1 here. If you end up in case 2 at any point, then you make this q1 equal to q2. So your current second query is your next iteration's first query, and then you again continue from step 3 and so on. Then again, if you hit step 1, you just break and start from the beginning. If you again hit step 2, then you continue doing that procedure. Every time you do step 2, you keep on removing 16.5%. So another very intuitive way to look at it is, every time you are doing this procedure, you are using one query to remove 16.5%, and every time you hit this case, you are using two queries to remove 33%. I mean, this is not exact, but it might help you think about it. So yeah, so effectively, okay, how did you prove it's 33% removal for two moves on average? So I can give you the intuition, you can work on the math maybe. So in the first reduction, there's a 16.5% reduction, right? So now let's use the range 1 to 100. I have also given a test dry run in the editorial as well. So let's say we get a greater than at 50. So, and then you query 33, right? So your two portions were 1 to 50 and then 51 to 100, rather 1 to 49. Now you, let's say, query at 33 and you, so this is the greater, and you query at 33 and you get this symbol. So now what is your range? Your range is now 1 to 32, which is this portion, plus like union 51 to 100. And this is the first query. Now where do you make the second query? You make it at the two-third position from the right, which is at 66, let's say. So 1 to 32. And let's say at the 66th position, you had got you had broken out of that case 2, you had got a favorable case 1 result. So let's say you get this result. Then you will have been removing this portion, right? So then your leftover part is 51 to 66. So how many queries have you used till now? 3. How much portion have you removed till now? 33 plus around 17. So you have removed around 50% using 3 queries. So per query you remove around 16.6%, right? which is equivalent to removing 33% per 2 queries. I mean, this is kind of a run through example. It might have happened that you are, so when this happens, you break, again, this is the favorable case. So you break out of it and you start from step 1 again here. But you could have got this symbol here and then you would have removed something 16.5% here, smaller thing, and kind of continued the algorithm. But you can kind of show, and I have given a brief formula in the editorial, that it's approximately 33%. Yeah, in the worst case also it's approximately 33%. So this, I think, gives you around 100 queries, which was enough to pass the best subtask. Maybe even less than 100 queries, I'm not sure. So I think it was like 98 queries. But yeah, so that bound on the number of queries wasn't too strict, so that some implementations, so that you don't have to make like worry about exactness of implementations. But yeah, it was, there was a buffer of 10 to 20, but this is the full solution. Any doubts in this problem? There was no canonical theory here that needed to be applied. It was just based on like thinking and trying out various approaches. Okay, so I'll assume then that this is done as well. Let's move on to the next problem. Oh, wait, I had already opened it. So for this problem, you are given a tree. So you are given a tree. So let me just mention a few prerequisites before the discussion of the problem. I will assume that you know small to large merging. I will assume that you know persistence and like segment trees. Again, links to small to large is given in my editorial. Even for persistent segment trees, there are multiple links given in the editorial. I will also assume you know about Euler tours, just like the DFS start time, end time, Euler tour of tree. Right. So in the problem, so every node has a color, right? So C1, C2, so on. So let's say this is yellow. Right, so every node has a color. Now you are in the queries, you are, let's say, given a particular node, let's say this node, and you are asked that in its subtree, within the depth D, rather within distance D, how many distinct colors are there? By the way, I think there was a color missing for this node. So this is what you have to do. Okay, so let's back up for a moment and think about what possible simplifications we can do for this problem. Maybe let's try to imagine this in the form of an array. Rather, let's think of it as this D distance that is given. Let's say this is non-existent. Okay, let's forget about this for a while. And let's say if we can solve just this inner rather in a subtree, how many distinct colors are there. Using the Euler tool, you can make this tree into a array, like flatten the tree. It's a very popular technique. And then each subtree query effectively becomes a range query, right? So it effectively becomes you have to answer for every range how many distinct colors are there inside the range. Now, our original problem was offline. Our original problem required an online solution. Let's see what we can do for this one. So here there are there are quite a few solutions. I think one offline solution is, and the most easy solution is using Mohs algorithm. So you can use Mohs algorithm to solve it. That is an offline solution with a complexity of order n plus q root n. A better way to solve it is using segment trees. So in the segment tree, you store pairs like this. I mean, not in the segment tree itself, but basically the problem reduces to if you can store pairs like for every I, you store I, comma, prev occurrence of color of I. Then the problem basically reduces to counting number of j between L to R. So let me call uh, this as x of I. So it basically means that uh, if this was orange and this was also orange, the index here was 18 and the index here was 17, or rather 16, then you, for this particular index, you form the pair 18, 16. Now in this scenario, the problem effectively reduces to counting all j between L to R such that x of j is less than L. Yeah. So this is all it reduces to. You can solve this using segment trees. How to do it and similar problems based on it all are given in the editorial again. Now, the complexity here would have been like you could do this using, I think, maybe just normal segment trees, or you could do this using normal segment trees offline. So normal trees plus offline sweep. So this technique is called offline sweep. So that just basically means that you sort everything maybe based on xj of xj, or like based on the xj's, and then you iterate over them and keep inserting values and then do the queries. The second method to solve this in online would have been using persistence. So if you can use persistence and persistent segment trees, you can solve this in online. Both of these take order uh, n plus q log n time to solve. This is better than n plus q root n, right? Now let's see what can we do if we want to incorporate this d condition into this segmentary solution. Like obviously square root n solution is offline, so it doesn't really matter for us. But yeah, so how can we include the d condition? The d condition effectively means that there is a cutoff depth below which you cannot look. You can only look between the depths of these. But this corresponds to in the array, it is not so uniform. So here it looks like a very nice uniform region that should be like easy to figure out. That's not the case in the array. In the array, the places can be actually kind of disjoint. And taking disjoint places and kind of finding this xj's based on only those disjoint places is kind of hard. And I'm not sure if you can even do this using this technique of storing prev occurrence of color of I, I pairs. Okay, but yeah, so let me just give you a couple of links if you want to learn about these. Uh, uh, these two blogs kind of discuss about how you can convert various queries into 2D point type things. So this is basically a 2D point, right? You have an X and Y point, and how you can answer queries and how you handle them using data structures. These are usually very standard problems, but there are not a lot of material available, like easily available on it, hence the blogs. But yeah, now if you want to kind of make use of these special locations, special disjoint locations that you get when you consider this um, extra dimension D here, maybe you can think of having merge sort trees where everything is sorted by their depths in a row. But even then, it's very hard to do and messy. So we need to think about some other way than flattening the tree and solving it. Okay, so here is the critical observation. Note that in this region, so this part looks very uniform, right? Everything is kind of in a few depths. So the main criteria here, whether a color is unique or not. So remember that even in the array case, we had derived a condition whether the color was uniform or not. That whether the previous occurrence of the color was inside the range, then it's not uniform. Rather, then it's not unique. My bad, sorry. And if it is outside the range, then my color is unique. So here also we will find such a condition. The condition here is if um, so condition if a vertex is unique. Okay. So I'll not say that a color is unique here. I'll say that a vertex is unique here. If um, let's say this vertex of V, we are considering about vertex of V, and let's say the color of V is given by C of V, then if for all J such that J was in J belonged to subtree of whatever was the query node, or let me write it a bit. So let's say our query node was U. Okay. So we say that a vertex V is unique if depth of V is max among all, let's say, vertices X, such that X belonged to subtree of U. Okay. And color of X was equal to the color of V. So this effectively means is that, let's say you have a subtree like this. Then for every color, let's say you have this yellow color here. Now there might be many occurrences of yellow in your node, in your subtree. Yellow is a bad color to choose from. Let me choose that. Yeah. So let's say this is the purple color. So there might be many occurrences of purple in your subtree. Among all the possible nodes which have the purple color and is within D distance, among all of them, you only choose one. Okay, and which is the one with the, rather not the max depth, it's the min depth, my bad. So you choose the one with the minimum depth and call it to be maybe, let's say, the representative of purple color in your subtree. Claim is you only need to keep track of the highest, the minimum depth node, because if you want to know whether a color, let's say this is maybe I think violet, if a color violet is in your subtree of U, if and only if the representative, let's say representative of violet, has a depth that is that has a depth that is less than equal to some depth t. What is this t? T is basically depth of U plus D. So if the depth of the representative of violet in your subtree is less than equal to this t, that means it's a valid node. That means this rep is valid. If it's not, then it's not valid. Any doubts till now? Like, at least for this condition, when a color is valid, when a color is not valid, and the fact that we are uh, counting the colors by counting the highest representative elements, kind of. So now what we do is, so essentially in your subtree, for every subtree, for every color, let's say for every color, you have a representative node. Okay, one question is, if you have two colored nodes, two of the same color nodes at the minimum depth, choose any one of them. It does not really matter. So maybe one idea is sort by depth and then sort by DFS time. Make any tiebreakers. Doesn't really matter. So yeah, for every color you have a representative node, right? So distinct colors equal to counting representative nodes. So representative nodes within the depth t, right? This much is clear. Counting number of distinct colors is just effectively equal to counting number of representative nodes that are within some depth t, which is again defined by depth of U plus D. Right. Now, how can we solve this particular problem? So, whenever you are kind of merging colors and everything, so this is a very common problem if you did not have the D thing. If you just wanted to count how many total number of colors there were, not distinct colors, just the number of total colors, then the most common way is to use small to large merging. Now, here we can just utilize that same kind of a technique to suit our scenario. So first, for clarity, like just to make it simple, we will not consider the online case. We will do everything offline, and we will just assume that we have to answer, like we know at each node what is the depth given and what value of D we have to answer for, and we solve it offline. What do we do for every node? We maintain this DS, so data structure, which stores set of representative nodes. Okay, sorted by depth. Cool. Now, as in small to large, you have a heavy child and you have certain small light childs. For this heavy child, you merge stuff into the heavy child. since remember that they only contain representative nodes, that means for every color there will be only one node of that color in your set. So if there is a tie, let's say there was a representative node of this green color here as well as a green color here, you choose the one, when you're inserting, you choose the one with has the minimum depth. So overall this becomes the set of this node, and it again just has the representative nodes uh, sorted according to their depths. So, and then just answering a query is just making a lower bound call in the set. So I am not specifying what the data structure is yet, but whatever data structure it is, it must support some kind of binary search, right? So if it supports some kind of a binary search, then we can find out till depth d what are like still some depth t, what are all the things, all the number of representative elements that are there. Let's say if there is k of them, then your answer is k, right? um, this is the offline version. Now let's look into the complexity. What will be the complexity? Well, small to large merging in is log n times you insert a certain element into any data structure, and let's say in our data structure we assume that you take log n time to insert, so another log n. So your complexity till now is n log square n. Okay. Now let's see what data structure we can use here. You might like to use a set or something, but one second. No, sorry. So let's say you can represent it by a set, but thing is, at the end of the day, you don't want to keep it as offline, you want to make it online queries, right? So supporting online queries in a tree scenario means that you have to like do some kind of persistence on the data structure. So a better option for this is maintaining it using a segment tree. Note that here you could have implemented something like maybe a tree or something of that sort uh, as a set. It would have reduced your memory, but the complexity is more or less the same for both of them. Both of them support binary searches, both of them support insertion deletions. It's the same. Your memory conditions would have been lesser for trees, like some set implementation. Note that you cannot really use STL set because you cannot make it persistent, but some any set implementation that you might have, you can make it persistent. So that's that. So let's just say you are using a segment tree to represent it somehow, um, and you make it persistent and blah blah, and then you can achieve this n log square n. So, and now since it's a persistent segment tree, that means every node has a version of this segment tree here. That is kind of what persistence is, right? So you can use online queries here, and this also solves the problem in n log square n time. This is not the full solution. You can even do better than this. How? In fact, I think the test data was made so that most of these n log square n solutions wouldn't have passed unless there was some kind of lot of optimization, maybe some clever use of hash tables. But yeah, how can you do better in a complexity? How can you do better complexity wise? Now, here you would also have to maintain. So let's look into what segment tree we would have to maintain here. We will maintain, and now let me just clarify one thing. Whenever you maintain a segment tree, it's maintained over an array, right? So there is an underlying array, and over it you maintain the segment tree. So let's say you maintain the segment tree on a depth array. What does that mean? It means that, let's say this array is called A. Then when you insert a node U, you make this change. You increment the depth of U position, okay? And when you remove a certain element, you again decrement the depth of U position. So how does this help? Well, remember that all the elements in your segment tree is a representative element, like whatever element you are logically storing, not physically, logically whatever you are storing. That means there are some elements like this at certain depths. Now, if you want to query everything that is less than equal to some t, or yeah, so what you are essentially going to query is this range, depth of u to depth of u plus d, where u is the current node. So this is kind of the range that you want to query in. So that will just correspond to this range. And whatever is the range sum here, that is your number of representative elements with depth inside this range. Hopefully this makes sense. For this segment tree, we are not maintaining what color these nodes are, right? So essentially you would have to maintain another set kind of to correctly maintain what color nodes which are, because you also want to remove certain nodes based on colors, right? If there are two nodes with the same color, you want to take either this or this, dependent on their depth. So you would have to ensure which color which is, and keep a separate data structure for that as well, maybe. Or maybe you can modify this segment tree as well to take care of it, to make sure that you can do this removal operation as well. Now, even if you could make this particular segment tree, so there are two parts now. One part, so part one, is showing that you can do all these. So you can merge all these information. Like the key point here is instead of iterating over all the elements and merging them one by one into the segment tree, like inserting them one by one into the segment tree, if you merge the two segment trees by simultaneously traversing them a bit cleverly, then you can achieve a total complexity of n log n. I'll show you how. But even if you could do that, you would still have to maintain another data structure which stores which color every node corresponds to, so that you can do these removal operations. And this might have taken you n log square n time, again using small to large. But so part one is going to be this. Part two is going to be how to know where to delete what node. Okay, so let's solve part two first. So for part two, we can notice something like this. So let's say this is our tree. And let's mark this with red. So let's say this node is red. This is red. This is red. This is red. Right. And let's give them a number as well. Now, for every node, we want to find its representative element, let's say. So for this node, 3 is the representative element. For this node, 4 is at a higher depth. So 4 is the representative element here. And this was the greater child, right? The heavy child. So notice that here you are, let's say you merged everything together. So you could have had multiple occurrences of representative elements, right? Now what you do is, except for one of the occurrences, all your occurrences will be deleted, right? Because let's say there was another child like this, which was also a red node. Then in here, this node would have been deleted from the representative element set for this particular node. Same for this, only this would have been kept. Same as you, if you try to go above, then here also the representative element is 2, here it is 1, and so on. So basically for every node, you have a certain ancestor. Okay, so for every node, you have an ancestor where it gets deleted from the representative set. Okay, so what if we could find for every node which ancestor that was? Then if we could find this in n, let's say n log n time, okay, then for every node we, let's say, store a group of values that we know that, okay, when I come at this node, then I have to subtract this from my representative set to, so as to ensure that condition that each color has one representative element in that set, right? So, and then we could just remove them one by one. And because we insert everything once and delete everything once, the total number of insertion deletions, it also is bounded by n log n. If we could find this, then it's very easy, right? I mean, not very easy, but the complexity will become n log n, right? Because we could do this in n log n. We can merge segment trees in n log n. Then the overall complexity is n log n. How can we find this? So let's say like the algorithm for this is sort every, so for a particular color, so fix a color. So let's say we fix the color C. Now for this, find all nodes and sort them by their depths. Okay. So let me draw a sample tree. Like this. And this is your red node. This is another red node. This is another red node. This is, let's say, another red node. This is a red node. Okay. Now sort by their depths and process them one by one. So when you are processing the ith node, you know that everything uh, that had everything with greater depth than depth of I has already been processed. Okay, so when I say processed, I mean, let's say you put them together in a some set of nodes. Here inside the set, you have them sorted by the start indexes. Okay, so let's say if this was 1, 2, 3, 4, 5, you have them sorted by the start indexes like this. Okay, and let's say you are currently processing node 3. So you come at node 3, you check the previous value, you check the next value, you find their LCS. So you find their LCS, and whichever LCA has greater depth, note that this is not minimum depth. You want the lowest common ancestor. So whichever of them has the lowest depth, which is with 2 in this case, that is where this 3 node will get deleted. Okay. Why is this true? Well, firstly, this condition should be self-sufficient because you will only get kicked out when there is something of a like lower depth. I mean, sorry, I think the inequality sign should have been less than equal to, my bad. Something that has lower depth can kick you out. Something with greater depth cannot kick you out of the representative set. And secondly, you have these sorted by their start times. Why is it like sufficient to just check only the previous and the next greater element? Well, you can kind of think of it intuitively. Maybe you can think of it in the form of auxiliary trees. But the basic fact is that anything which has like some other start time, that will have a higher LCA than the best of these two. So this is how for every node. So how are you effectively maintaining this set? This is just an STL set. Okay, this is just an STL set. You process this one by one and you put it here. The previous and the next are just iterated plus 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 and iterated minus minus, and you can find the LCA in logarithmic time. So this is how in n log n time, for every node, you can find where I delete that node. Right. So if you know where you delete that node, you can take care of this minus minus operations. The plus plus operations are very simple. When you encounter a new color, you just make it the representative color, right? A representative node of that color. So you just do a depth plus plus at the particular depth that you're standing on. Now, the part 2 is then done. How about part 1? How can we merge two segment trees very fast? So note that in small to large, what we do is you have a segment tree, you iterate over the values of the other segment tree, and you put the elements here one by one, right? This takes n log square n time because segment tree insertion is n log square n. Now, here is what I want you to do. Let's say, okay, so one thing that you should note here is whenever we are using small to large and segment trees and persistence, we are always talking about dynamic segment trees. Dynamic segment trees are that variant where you only create a node when you need to create that node. Because imagine in these segment trees, if you have 10 to the power 5 nodes everywhere, then obviously we'll get a memory limit exceeded. Now, in most of the cases, let's say for the leaf nodes, okay, for the leaf nodes, there's only one node that you need to take care of, right? All the other nodes are kind of, so there is only one path from the root of the segment tree down to your leaf node. The rest of the pointers are useless, correct? So that's kind of the main motivation behind dynamic segment trees. To store n values, you need n log n data. So what you do is, when you want to merge two segment trees, okay, which effectively is the same as taking care of um, all the insertions, you simultaneously traverse both of them. Okay, so let's say you are let's say you are standing here, you are standing here. You see that there is no right child, there is a right child here, but there is no right child here. Then in your new segment tree, you attach this as your right child. Then in the left child, you see that, okay, both have a left child, then you go down to the left child. Now here again, you see that both have a right child, so you both go down to the right child, and you obviously attach them in your new persistent version, because obviously you get a persistent version. And for the other node where there is no child here but there is a child here, you do the same thing. You attach this node, sorry, you attach it to this particular node. Okay, so the main point is you only visit those nodes where there is a corresponding node both here and here in both the trees. And where there is a null pointer at any one of the children, you just take this and attach it here. Okay, now for a second, forget about persistence. So persistence, forget about it. Let's say we are just merging these two segment trees. Obviously, after the merge operation, you will get a new segment tree that is the resultant segment tree for a particular in your tree, whatever tree there was. So let's say this segment tree was T1, this segment tree was T2. In your original tree, this was the T1 node, this segment tree had the T2 node, and here you get the T1 union T2. This T1 union T2 you are getting through here, right? Now, claim is over all such union operations, the total complexity will be n log n. Why? Here's why. Consider, so I'll explain this in the form of a potential function. So consider a potential function which just stores sum of secretary sizes. Okay. Initially, what is the value of the potential function? Consider a tree, consider a star graph, star tree like this. So for every one of these, they have a segment tree, let's say Ti, correct? So they have a segment tree Ti. How many nodes are there in the Ti segment tree? There is one value that you have inserted. That means there are log n nodes created from root all the way down to the value, like the leaf representing the value. So initially the value is n log n for P. Now what happens when you merge two nodes, merge two segment trees? every time you travel two corresponding nodes, you merge them into one, right? So when you travel two nodes, you merge them into one. So you effectively discard one node. Make sense? So for every two nodes that you travel, you discard one node. So your P decreases by 1, right? Now how much can P decrease? N log n. That means how many total nodes that have you visited? 2n log n. During the merging steps, it will never happen that you visit one of the nodes here, which is where there is no corresponding node in this tree. Whenever you visit a node, that means in the other tree also there is a corresponding node. Hence, you always visit nodes in the form of two nodes simultaneously. And for every such two nodes that you visit, you discard one node. And since you can discard only at most n log n nodes, that's why your complexity is still n log n. Note that this is just during merging. Apart from this, you also make n insertions, so you need n log n, and you also make n deletions, so also n log n. These were basically the complexity that we were getting. Where did I show part 2? These were the complexity that I was getting here. Like, you can find the depths, you can find the pad to remove in n log n, and you have to actually remove and insert in n log n as well. So overall, all the operations are n log n. So yeah, so that's why the overall complexity is n log n for the problem. So you are just merging the segment trees in a clever way, even in small. So it's not, you are not directly using small to large here. You don't even have to know which segment tree has the greatest size, because whatever size it is, when you do all the mergings, uh, this is always true, and that's why you make n log n operations. So any questions for this problem? Hopefully not. So I guess this problem is clear as well. Then we can move on to the last problem, which was PPARTS. Right. So here you are given certain integers. You are given bi integers, each of value ai. You have to choose some integers, and each group of integers have some color. You have to choose number of partitions of I, which means the sum of the integers that you choose has to sum up to I, and how many such partitions are there. Partitions are different if there are different colors involved in the partition. So for this, a DP solution might be possible given that there is not this B condition. I mean, with the given constraints, there is no DP solution, but maybe for simple cases, there is a DP solution. We will directly jump into the intended solution. So notice that we are given that for all I, let's say we choose, so for color I rather, for color I, let's say we choose J of the occurrences. Then AI into J, summation over all I, has to be equal to, let's say, some number n. So what is n? N is basically the partition of I am denoting it by partition of n. Rather, let me denote it as small n. Small n, and we will have to find the answer for all n from 1 up to n. Okay. Now what do we do? Here the constraint is that j has to be less than equal to bi. Okay. So one common way that we often approach these sorts of problems is by analyzing these as multiplications of power series. So for example, here let's say we have the for every color, let's say 1 2 3, the ai values were a1 a2 a3 and bi values were b1 b2 b3. So for a moment, assume that all bi is equal to infinity. Then your problem simplifies like this. We have to find the coefficient of x to the power n in the following polynomial multiplication. A1 plus x to the 2a1 into again 1 plus x. So if we could expand this entire thing, and find the coefficient of x to the power n, that is just our answer. Okay. Now what we do is, bi are not all infinity, right? We are given a certain upper bound on b's. So what we do is, now we can reduce this problem to a case where we are given some infinity. So why we are trying to do that is, if the bi's have had some upper bound, then it would have been essentially like this: 1 plus x to the, rather let me denote this as a summation. So this is some x to the j ai, right, for j up to bi, sorry, j up to, like, whatever j, you can have up till infinity. So there is no condition here. This is basically this sum, right, this polynomial, rather this formal power series. What you can do here is, if there was a certain b condition given, then it would have been like this: summation j till bi x to the power j into ai, right? But then this is not useful. Like this, you cannot really work well with this. Why? The main motivation behind writing it as these kind of infinite sequences, infinite formal power series, is that if you have this sequence 1 plus x to the power a plus x to the power 2a plus so on, this entire thing sums up to 1 by 1 minus x to the power a. Okay, so that is why you can represent an infinite thing using a finite thing. In this case, you cannot write it like this. So what we do is, we have this 1 plus x a1 plus x 2a1 plus x 3a1, let's say up to infinity, but we subtract x to the power b1 plus 1 a1 minus x to the power b1 plus 2 a1 and so on. Okay, so it's still sum of two, like it kind of involves two infinite sequences, but it is equivalent to this. Now what do? We take x to the power b1 plus 1 a1 common, and then this part essentially becomes equal to this part. So let me just denote it as s. So it becomes just s, and you have s minus this. So this entire expression becomes 1 minus x b1 plus 1 whole into a1 by 1 minus x to the power a1. So this we can write this this formal power series, this formal power series as this. So here instead of a1, what is it that we have to do? We have to take product over this for all ai and find, and inside this for all ai, for all I, and find the coefficient of x to the power n, right? Because this product notation is effectively just what I've written here. Now it was pretty easy to derive this formal power series expression. The key part here is what to do after this. How do we compute this? The key insight is, let's say we denote this thing as f of x equal to right. Let's say this is f of x. Then we take log of it. So ln f of x equal to this power, this product thing becomes a summation. So you just have 1 minus x to the power bi plus 1 bi, right? Ln of this minus summation ln of 1 minus x to the power ai. Now the second thing, we need an important formula here, that is this. The expansion of 1 minus x is, I think, given by minus summation x to the power I by I. Let me just recheck this just to be sure. Yeah. So for 1 minus x, it's summation x to the power I by I. Then for, if you substitute 1 minus x to the power a, what will it become? Minus summation x to the power j into a by j into a, where j can vary from 0 to infinity, right? Now here's what we need to notice. Firstly, these two are of the same form, right? Both of them corresponds to this form. Now you can group together all of the 1 minus xi things that have the same power here. Okay, so I mean, these might not be seem to be the same, but I mean, this will have some numerical value, right? Some, let's say 7, 8, 11. Here, let's say the values are 11, 12, 17. Then you have a total set of 7, 8, 11, 12, 17, and you can figure out how much you need to, how many times this factor appears, and have a frequency array like that. And then for every one of them, you compute this thing. Notice here that this might seem to be an infinite sequence. I mean, it is, but we only care about the number of terms such where the power is less than n. So j into a is less than n. Now, once you have this kind of a set, that means you are effectively going from 1, 2, 3, 4, 5, up to n once at most. and then you are iterating over the jth like all the multiples of that number. That means this effectively becomes n log n, right? Because how many times do you include this summation in your whatever so this will give result to a polynomial, let's say p of x. Okay, right? Because like a polynomial in x, and for every coefficient you know what is, like for every power of x you will know what coefficient to put using this formula, like using this expansion, and you will overall need to iterate over them n log n, because it's basically n by 1 by 1 plus 1 by 2 plus 1 by 3 plus 1 by 4 plus so on. So the number of times this j needs to iterate is n by a, hence this thing. So this effectively reduces to n log n. So you need n log n time to compute this p of x, and then you can do in n log n e to the power p of x, provided that you are only like taking care of the first n factor, like the first n powers of x, and then you can get f of x. This is f of x. F of x is essentially what you wanted, right? The n coefficient of x to the power n in f of x is your answer for n. When you get f of x, you get coefficient of all such x to the power n, so you get the answer for all the values. You can see the setter's code or the tester's code. Most of it is just library code to copied from like I mean taken from CPA algorithm or some other sources. But yeah, it's mostly library code, and the main function is just 7 to 8 lines. This is the only library code that you need, and taking the log and iterating over this is also pretty easy to do, like to implement. So this was the intended solution. Read the editorial if you have some doubts and want some links to study up more. So I've given 3 or 4 links where like links to Codeforces, links there in the Codeforces link. There is a link to a book as well where you can study up more on this. So yeah, that's it for today then. Okay, okay, let me just give a brief what my ideas are for the challenge problem. I have not looked at all the solutions yet, but what I think should get many points, and it does, is a kind of a 2D binary search. So you are basically trying to figure out which parts have a 1. So it's kind of like a parallel binary search if you can do it. So basically you have the entire range. You might query the left subpart and the right subpart and go inside to find the left subpart and right subpart only if you see that you have a non-zero count. So this is for a linear array, right? So for a linear array, you can kind of recursively build, like divide into subparts and then only go inside if you get a non-zero value. Now, for a 2D grid, a way to do it is, first thing you can maybe check per column or per row, or you can check using like this. So you divide it into 4 parts maybe, and then go into each of them recursively if you have something there. Now there are multiple optimizations on this. You can use prefix sums in multiple places to optimize. There are so a few of the solutions use some harder techniques to. So what they do is use this kind of a technique for high value of p. So for the p equal to 15 case maybe, and for the low values of p, they have some other methods where they go row by row and then try to figure out which all places have a 1. But yeah, it's a heuristic based problem. I mean, there is not one single best solution for this. So hopefully I'll get the editorial done by this week and you can see it there. So that's it for today. Thank you guys.